Okay. Okay, good afternoon or good morning. First, I would like to thank the organizers for such a nice convention and that gave me the opportunity. Second of all, for the nice and big efforts of the chef that make it so interesting, the amounts of food that we had here. And I will try to do it short and interesting, or at least one of them. Okay, this talk is going to be about unusual properties of magnesium oxide nanosheets. The outline will be at first about a theoretical background, then some methods to prepare magnesium oxide. Then I will show you some unusual properties and summary. So magnesium oxide, you can find it in different disciplinaries such as health, it's anti-sedite, engineering, it's fire resistant. In plasma display panels, it's insulator, and also it have a very good transmission in the UV, in the visible and IR, and also it makes Ahmadinejad very interesting because it's in order to immobilize the radioactive waste. But none of this is the reasons why we started to investigate or research magnesium oxide. Our research started with hafnium oxide. A few years ago, there were some theoretical calculations that shows that diamagnetic materials, such as hafnium oxide, can exhibit ferromagnetic behavior. This is due to point defects. 2 years after, our group published, Einat Tirosh and Gil Markovich published a paper that they showed that hafnium oxide can exhibit ferromagnetic behavior. Similar theoretical calculations were done for magnesium oxide and calcium oxide, and it seems like a good experimental challenge, and this is our research. So during this talk, I will mention the word defects, so I would like to elaborate on defects a little bit. We have three types of defects. The first one is point defects. You have point defects have this type. You have vacancies and substitutional impurities. And when we are looking at magnesium oxide, you can see that we have a number of vacancies. Vacancy, it's absent of atom. And you see that we have a P center, which is the absent of magnesium and oxygen. You have a F center, which is absent of oxygen vacancy. It's an oxygen vacancy, and a magnesium vacancy called a V center. Another type, it's linear defects, which it's a group of atoms in a regular position, often called dislocations. The third type are planar defects, which is the interface between homogeneous regions of the material, often referred to the grain boundaries in the material. Now, the properties of the material the band gap often change or indicate what will be the properties of the material. You can see the different band gaps will give different properties of the material. Now, magnesium oxide have a large band gap. This is why it's an insulator. It have a large dielectric constant. And when we are looking on the band gap, when we are looking about properties like photoluminescence, it's when we are using light in order to excite electrons from the valence band to the conduction band, or we look on the cathodoluminescence, which is to use electrons in order to excite electrons from the valence band to the conduction band, and then we're measuring the luminescence when the electrons are decaying to their ground state. Magnesium oxide don't have it because the band gap is too large. The band gap of magnesium oxide is 7.3 electron volts. Also, magnesium oxide is diamagnetic. Now, some theoretical background. Magnesium oxide have a FCC structure and is assembled from magnesium and from oxygen. You can see the energy levels. You can see that the valence band are mostly from the oxygen levels, and the conduction band is from the magnesium levels. Now, when we have a vacancy, we can have a localized energy level that will be inside the band gap, or lowered from the conduction band or above the valence band. Another type of vacancy can give you another position inside the band gap. Now, there were a few theoretical calculations that show what type of vacancy will have what kind of energy. It means that if you have an F center, the new local energy will be about 1.2 electron volt under the conduction band. Another type, V center, will be 0.3 electron volt above the valence band. And there were a few theoretical calculations. Now, if we will look again on this same model, but this time we will take into account the spin of the electrons, we see that in magnesium oxide, all the spins are paired. This is why it's a diamagnetic material. Now, again, if we have a vacancy, there can be that the electron will be trapped inside this vacancy. Now we have an unpaired electron, and we can have a paramagnetic material. If the vacancy density or the concentration of the vacancies will be high enough, and with certain conditions, which I will elaborate on them, we can have that the spins will have the same directions in order to minimize the energy of the crystal. Then we will have a ferromagnetic behavior. This effect is defect-induced magnetism, and this is what we are trying to have. If we can see a magnesium oxide crystal without defects, you can see that you don't have a localized magnetic moment, and there is no localization of charge. And this is essential in order to have ferromagnetic behavior. But when we have a magnesium oxide with defects, then we have a localized magnetic moment because we have electrons that are trapped inside the vacancy. And if the defect or the vacancy concentration is high enough, we can have a delocalization of charge that the percolation threshold between the electrons will be close enough. And again, we will have defect-induced magnetism. Now I will elaborate on the methods to receive, to prepare magnesium oxide. Usually, in order to prepare magnesium oxide, you need to take alkoxide, to add water or another solvent, to receive magnesium hydroxide, to heat the sample, and then you have dehydration, and water goes out, and then you receive magnesium oxide. It took us about 6 months, and we developed a synthesis that goes straight to the magnesium oxide without the magnesium hydroxide. Now, this stage gave us, or this synthesis gave us a very defective nanoparticles. They have a lot of dislocations and a lot of vacancies. Now, in order to eliminate those dislocations and to eliminate those vacancies, we anneal the sample at 750 Celsius. And this eliminates the dislocation and the vacancies. Some of them, not all of them. So now we'll show some results. First, you can see here with this diffraction pattern that our particles or sheets that I will show you later are crystalline. You see the diffraction peaks of the different planes from the magnesium oxide. And when we started to investigate the different particles that we saw that there is a dependence on the lattice parameter with the change of the grain size. We saw that smaller grain size have an extended lattice parameter, which you can see that it's about 2% change of the lattice parameter. Then, when we took a sample from our synthesis, which is a colloidal synthesis, and we took a reference sample, which we took magnesium, burned the magnesium, and we took then the smoke, which the smoke here, it's nanoparticles of magnesium oxide. You need to understand that our synthesis, the temperature is about 300 Celsius degrees, and when magnesium burns, it's about 3,000 Celsius degrees. So you can see that when we took our sample to the SEM, you can see here that you have a very nice cubic particles, and you see that our sample have a different morphology. But when we took it to the TEM, you can see something very interesting. Here you can see the reference sample, the magnesium oxide that was burned, and here you can see our sample. Now, you can see here there is a high periodicity, and here we don't have it. A good measurement for the periodicity, as Kobi Barkan explained, it's the fast Fourier transform. So we use the fast Fourier transform in order to see the periodicity. Here you see points. It's like the diffraction points. When you have points, it means, in other words, you have high periodicity. You see that our sample, we have points, but the points are stretched. It means that you have a lot of different orientation of the planes. In order to see, when you take a reference sample of amorphous carbon, which of course you don't have any periodicity, you don't have any points. So again, when we look on our sample, this is the reference sample. You see that the planes are parallel, and there is a high periodicity, or long-range order. When you look at our sample, you see that there is no high periodicity or long-range order, and you see that we have a lot of dislocations. When we looked on the morphology of the magnesium oxide, we saw something very interesting. We saw that we have a sheet-like morphology. This is a two-dimensional sheet. This is another one, and this is another one. Now, first I will show you that, of course, here it doesn't look crystalline. It looks like something amorphous. But when you go to high-resolution TEM, you can see that it's crystalline. Here the resolution is quite poor, but again, when you use the fast Fourier transform, you can see again that you have the different diffraction points. Now, you need to understand that it's very, very unique to have a two-dimensional sheet morphology in a colloidal synthesis. And why is that? Because when you have a synthesis, you have particles that floats inside your solvent. They will try to have the minimum energy. This is the minimum surface-to-volume ratio. This is why you will try, or they will assemble as a three-dimensional particles. In our synthesis, what happens is, again, because it's a colloidal synthesis, you have a lot of cubic that floats. And what happens is that you have a two-dimensional sheet. It's not, like intuitively, it won't give you the minimum energy as a surface-to-volume ratio. But it was seen before, 3 years ago by Kotov with cadmium telluride. And he explained that in order to have it, you need to have a few forces, and you need to have a large dipole moment. Okay. So again, you can see here that the building blocks of those sheets are about 3 to 5 nanoparticles of magnesium oxide. But what happens is that in situ, during the synthesis, they are assembled to two-dimensional sheets. And here you can see it's an illustration, but the sheet is assembled from a lot of small particles. AFM topography that was taken by Dennis and Yuri from Orchishnovsky lab shows that the morphology is that you have here about 3 nanometers building blocks, and if we have a sheet that another layer of sheets was laid above it, so you can see that the difference. You can see 3 nanometer height and then another 3 nanometer height. You can see you can distinct between the two sheets. So this is just to remind you that there were few theoretical calculations with different defects can give you a different position inside the band gap. You can have a lower localized energy level. And you need to understand that every energy here can be observed as emission in photoluminescence or cathodoluminescence. So this is, again, the reference sample, the magnesium oxide that we burn magnesium. And you see there is no cathodoluminescence. Again, this is due to the large band gap. But our sample exhibits cathodoluminescence. Again, this is the first time that the measurement of cathodoluminescence from magnesium oxide nanoparticles was seen. The different lines depend if the magnesium oxide was annealed or wasn't. Here we have a photoluminescence of the magnesium oxide before annealing. This was published only 6 months ago from a group in Berkeley, that someone was able to see photoluminescence from magnesium oxide nanoparticles. Now I will show you the ferromagnetic behavior. But before that I will show you, I need to note that I know that impurities can give you ferromagnetic results. This is why we did some countermeasures. Or we did the follow to be sure that the ferromagnetic signal is not due to impurities. First, we used a high ultra-pure magnesium. We did some analytic measurements, ICP, in order to see that there is less than 2 ppm of iron and manganese. And of course, we did magnetic measurements to the precursor, and we saw that it's diamagnetic. This is remanent hysteresis. For those who don't familiar with magnetism, it means that it's ferromagnetic. And this is, after annealing, you can see that it lost its ferromagnetic behavior. We wanted to be sure that if we have magnetism, probably it's due to mobility of charges. So we measured conductivity. We saw that when we are, first you need to see the value is 1 and minus 11, the theoretical value of magnesium oxide. We received 10 and minus of 9. But when we started to hit the sample to 150, we saw something very unique. We saw that when we measured back the conductivity, we saw that it drops partly to 0. And we wanted to see what happens in 150 that suddenly it changes its properties in conductivity. And we saw that there is not a change, so dramatic change in the grain size. It's in the temperature of 600, 700, but there is a dramatic change in the lattice parameter in this temperature. So we know that there is a connection between the change in the lattice parameter and with the conductivity. Now we'll summarize. We received magnesium oxide in colloidal synthesis. Then we saw it have a very unique morphology of two-dimensional sheets. We saw the different height of the different grain size that assembled the sheet. We saw that it exhibits cathodoluminescence and photoluminescence. We saw that it exhibit a ferromagnetic behavior, and also it exhibits conductivity. The take-home message is crystals are like people. The defects are what make them unique. And one more thing, I would like to thank a few people. First, I would like to thank Gil, my advisor, and of course, a special thanks to Einat Tirosh, she's here in the audience. And of course, all of those people, because it were a lot of measurements, so to Ina Popov, to Yuri Rosenberg, Yossi Larea, Larissa, Anna, Maya Barsadan, and Lev Weiner in Weizmann. Now we're doing also EPR measurements, and we hope that we will do STM measurements, again with Dennis and Yuri, with Ori Chishnovsky, and of course to all the group collaborates. Thank you.
Ferromagnetic properties. Do they disappear at around 150 degrees as well?
Celsius or Kelvin? It depends, because the change is that the ferromagnetic behavior is usually we can see it till about between 150 Kelvin, and the conductivity disappears in 150 Celsius. So we can't correlate between the magnetization.
You only have those magnetic properties when you cool?
Yeah, we do the
Temperature there are any?
in room temperature. No, you can't see any ferromagnetic behavior in room temperature. Usually, it disappears in about between 150 Kelvin.
Wow. Okay.
Yeah, the remanent. Okay.
You have to distinguish between the annealing temperature and the temperature of appearance of ferromagnetism.
Okay. Now, there's a sort of a Curie temperature around 150.
Yeah.
Yeah. So you see that the remanent here it's in 10 Kelvin. Yeah, and you see that here the remanent is at 2 Kelvin. So even if there was something, we should see it. We should have seen it.
So this hysteresis loop seems asymmetric.
Yeah. No, we don't know why. Also, it's very hard to explain the mechanism for the magnetization, although we know it's supposed to be from vacancies, but we believe also that it's from dislocations. And we don't know exactly what is the mechanism, and we don't know explain exactly what the asymmetry of the loop. But if you have ideas, I'll be happy to hear some. I couldn't hear. Of the what? Of the structure is okay. The synthesis, it's a colloidal synthesis. So at the end of the synthesis, I have a powder of magnesium oxide. The powder is assembled from nanosheets. So I don't know. I guess that the structure is nanosheets. It doesn't change. Yeah, it's FCC. It's FCC. Yeah.